Let's take an example of a diode that's connected to a noisy voltage source through a 10 kilo ohm resistor. And in this example, we're going to have that the voltage then is equal to, it's a 10 volt DC source, but it has a 1 volt sinusoidal oscillation on it. So we can draw this maybe in a little more familiar form as our DC source here, we'll call it V sub S is equal to 10 volts. But it has superimposed on it a, call it lowercase v sub s of t equaling 1 times the sine of omega t. And it's driving a 10, or through a 10 kilo ohm resistor, it's driving a diode. And we're asked to determine the small signal voltage variation on this diode due to this 60 cycle per second ripple on our 10 volt source. We're going to do this in 2 steps. We're going to first determine the DC component. And with that DC component, we'll calculate then R sub D, the incremental or the small signal model resistance for the diode. And then we'll calculate that small signal, the results of that small signal ripple at the diode. So first of all, in the DC, we have our 10 volt source through a 10 kilo ohm resistor driving the diode. And we need to determine the current I sub D here so that we can calculate the that incremental resistance. Now we're free to use any model we want. We can use and iterate on this and use the exponential model and iterate on this, or we can use the constant voltage model for the diode. We're going to use the latter, and frequently that's going to be the case in these kinds of circuits. We're not looking for exact precision in this. We're just trying to get a model, and a model by its nature is somewhat inaccurate. So let's use the constant voltage drop of 0.7 of a volt across here to calculate I sub D would then be the 10 volts minus the 0.7 volts divided by the 10,000 ohm resistor gives us an I sub D of 0.93 milliamps. With that, we can calculate the incremental resistance. R sub D then is just equal to the thermal resist or the thermal voltage divided by the bias current, I sub D. So this is going to be 25 millivolts times 10 to the minus third divided by I sub D, which is 0.93 milliamps times 10 to the minus third. And that gives us R sub D is equal to 26.9 ohms. Alrighty, with that, we're now prepared to do our small signal model, where this now is 1 volt times the sine of omega t going through the 10 kilo ohm resistor to our diode. But now, because we're using the small signal model, this diode we're going to model with as a resistor value R sub D equaling 26.9 ohms. We can calculate the small signal ripple, the voltage ripple across the diode due to this ripple in the noise, using a voltage divider. So we're going to get small signal V sub D of t is going to equal the sine of omega t times R sub D, which is 26.9, divided by the sum of the two resistances, 10,000 plus 26.9. And when you go through and calculate that, you get then that the small signal voltage variation on the diode is equal to 0.0268 sine of omega t, or the small signal ripple there is about 26 millivolts. Compared to the 0.7 of a volt ripple on the diode, that is a relatively small quantity, and we're justified in using the small signal model. We could then write the total voltage, which would be V lowercase v sub uppercase d, then would equal whatever the voltage is across here. We've assumed that it's 0.7 of a volt, so 0.7 plus 0.0268 sine of omega t.